All right, welcome back. To go over our notion of statistical significance testing with System A versus System B, I want to take us a step out of this world of computing and the artificiality of that to something that's a little bit more concrete. The same notion. We want to know if something is better than something else, but something that we can sort of talk about a little bit easier than information retrieval systems. So let's look at this question: who is faster, Usain Bolt or Justin Gatlin? These are two very fast sprinters. I believe what I have here are times for the 100-meter dash. I went and I looked up for Usain Bolt and Justin Gatlin race times over the years. Now, let's think about this question, though, before you look at these race times. Who's faster, Bolt or Gatlin? One way to approach this problem would be, well, let's go have Usain Bolt. You go run 100 meters, and I'll time you. And then, hey, Justin, you go, Justin Gatlin, you go run 100 meters, and I'll time you. And we could measure their times and see who runs 100 meters faster. Well, first of all, you might very well say, well, wait a minute. What's really the question we're trying to answer here? And you go, well, overall, who is the faster runner? Okay, well, who's the fastest runner? Well, I wouldn't want to just do one measurement of Usain Bolt and one measurement of Justin Gatlin. You'd say, obviously, especially if they ran at different times, Usain Bolt could have had a slight tailwind, Justin Gatlin a slight headwind. Now, not enough that we would, say it was, somehow it invalidates our results, but it would affect things, okay? So it would be really, really nice. And likewise, maybe Usain ran where his home track was, and it's got a slightly different surface than the home track for for Justin Gatlin, where he ran. That could affect things. Maybe just the day that we had Bolt run versus the day we had Gatlin, because maybe they don't run on the same day. Maybe one of them was feeling better than the other. Maybe if someone ate something, or maybe they had gone out the night before for a good time. Who knows? All of a sudden, before we do it, we were like scratching our head going, there are a lot of factors at play here. A lot of random things that could change. The headwind, the temperature, the track surface. Well, and even this weird notion of you go run 100 meters by yourself and you run 100 meters by yourself. If you spent any time watching track, you know that runners, it's very important to them to compete against each other. Yes, a 100-meter dash is just an all-out effort, certainly, but this notion of you're against other people really affects your motivation and your push and your power, and you can push yourself harder racing against people than you can usually most people than racing by themselves. I mean, this is why, for example, in bicycling, they've got a time trial event. And the idea is, well, yeah, we're not going to have you drafting each other, but also it's just you against the clock. It's a mental challenge as well. So for running, it certainly is going to affect things, whether or not, maybe Justin had someone to race against and Bolt didn't, Usain Bolt didn't. So wow, you all suddenly go, I don't really want, I want to try to eliminate all of those factors as much as possible. I'd like to be able to compare them under the same conditions. And indeed, there are races that Usain Bolt has done that Justin Gatlin hasn't, and races that Justin Gatlin's done that Usain Bolt hasn't had. Does it make sense to take a time from one of Justin's races that Usain didn't do? Maybe, and we could maybe use that data, but wouldn't it be nice if we had some way to basically be like, I have times from these racers under the same conditions, and so all those random things I can ignore because they were the same for these measurements. They ran on the same track at the exact same time, so they had the exact same wind. They were running against the exact same competitors, so they had the same motivation. All of that, and all suddenly, wow, I don't need to try to account for that variance in my understanding about what's going on because I measured it at the same time. That is called doing a paired measurement, okay? We measure them both under the same circumstances. And that's actually what I have here in this table. I found 9 races where Usain Bolt and Justin Gatlin raced against each other at the exact same time, and they received these times, okay, for the races. These are in seconds. This is a very short, fast race, very fast. All right, so the great thing is when they ran in 2016 at Rio, we know that Usain Bolt took 9.81 seconds, and Justin Gatlin was 0.08 of a second slower. I mean, it's amazing. There's so much. Here, Justin Gatlin was 1/100th of a second slower. All right. Does Justin ever beat Usain? Yes. Here in Rome, he beat him by 1/100th of a second. All right. These are true competitors. All right. Now, so that's neat. This pairing eliminates a huge amount of variability that we would have to otherwise sort of understand and account for in trying to decide, was it just noise that led to these results, or was it something else? So here, our variability is down to the individual races. We've got the same people, we've got them, all the tracks at the same time. So the only thing left is these separate events are different. They are different times, different places, different weather, different times of the year, different parts of the training cycles, where, depending upon what the major races are, Olympics and so forth and so on. So that all of that's been eliminated, and we're just left with these 9 identical moments where they raced against each other. Now, you could just say, oh, what I want to do is, well, let's go ahead and let's do a summary statistic. Let's take the mean, also known as the average. We're going to take the mean here, and the mean for Bolt overall is 9.81, and for Gatlin, it's 9.93. All right, Usain Bolt, by the summary statistic, by our test statistic, is faster than Justin Gatlin. So, and is that a significant difference? I would say in the 100-meter dash. Oh, absolutely. I assume this is the 100-meter dash. I should have really have written it down somewhere. Yes, it is the 100-meter dash. Anyways, so that's a pretty big gap. Is it statistically significant, though? Could this have occurred by the randomness of the fact that I only have 9 measurements? Okay, that's our next thing that we want to understand. Well, what we want here, by the way, as we said already, was we don't really want to think of it as take this pile of numbers versus this pile of numbers. We want to talk about it at the individual line level. So this versus this versus this, and so forth. And so what we really want to do is take the difference between the two. So when we take the differences, the way I have them written here, where we are going to subtract Gatlin from Bolt, we get minus 0.08, then we get minus 0.01, then we get minus 0.04. I guess I could just look at the numbers. 0 minus 0.06. Come on, Justin, can you ever beat him? Minus 0.08, minus 0.01. Oh, and then actually, oh, wait a second. I had, oh no, those are, sorry. Gotta get my, this one he did beat him. All right, so that's positive. And then we get minus 0.16, minus 0.36, and minus 0.32. I will, by the way, we'll note here that Justin Gatlin certainly seems to have narrowed the difference over time, by the way. Now, we would take these differences, those are what we really care about. It's not the mean here and the mean here. The interesting thing is, if we take the mean of the differences, it's the same as taking the mean and subtracting the two, okay? But we would really care about these differences we're using our statistics. So we'd be paying attention to these numbers. And I want to note something. We could apply different test statistics here, different ways to compare these. So we could instead replace the mean by the median. And when we take the median, again, we don't want to take the median here and the median here. What we want to do is take the median of all the differences. Same way, we could try other statistics as well that we apply, but we would apply them to the differences because it's at the paired level that we care about, because at the pair we've eliminated these all this randomness. My favorite example, by the way, I like this example, but my favorite example about understanding the notion of doing paired differences is in textbook. Actually, I have it over here. Let me see if I can grab it. This is off screen. Oh no. This guy, you can't see, but it's Statistics for Experimenters by Box Hunter. Absolutely fabulous textbook on how do you run experiments and do statistics on them. The example they have in there, so this is Box Hunter's example, is you have a manufacturer of shoe wear. Let's say sneakers or tennis shoes or running shoes, whatever, some sort of casual footwear. And rubber compounds can be either tough and hard wearing, but then they tend to be slippery, or they can be soft and have lots of traction, but they also tend to wear fast. So let's say you formulated a new rubber compound versus your old one to improve its performance in some measure, and you want to test this. You want to test it in the real world with real people using the shoes. You could give half the people shoes made with compound A, rubber compound A, and half the people shoes with rubber compound B. But the problem is some people weigh more than others. Some people walk with different gaits. Some people have one leg that doesn't work as well as they want it to, and so that gets more wear on their shoes and this and that. So how could you eliminate all that variability? Well, the idea is, what I'll do is I will manufacture for everyone a pair of shoes, but on one shoe I put compound A, and on the other shoe I put compound B. Now as that person walks around, each shoe gets exposed to the same surfaces, the same weight. But you go, well, wait a minute, what about that some people might walk differently with the right leg versus the left leg. What if, we know people are dominant and with their right leg, maybe all the right hand shoes would have more wear than the left hand shoes. So what we do there is across everyone, by the way, we randomly choose whether it's the right or the left shoe for them to actually receive which rubber compound on which shoe. So we can pair things up to eliminate variability, and where we cannot eliminate the variability, we can use randomization. So that's a wonderful example. But again, the nice thing is now we can get differences between the pair of shoes that someone wears and take all those pairs, and we've eliminated a huge amount of variability, and this will improve our ability to detect whether something is statistically significant difference or not. All right, nevertheless, we've got Gatlin's. Appears as though he only beat Bolt once. Nevertheless, let's just work through this to understand what it means to find out whether something is statistically significant or not. Maybe we don't have enough evidence here yet. Maybe these times are too close for us to really tell. Okay, so how do we go about this? Well, the we're going to use null hypothesis testing, and immediately we say this null hypothesis. Oh, geez, if that doesn't just make your brain curdle and go, I don't know what null hypothesis is and means and so forth and so on, then don't fear that, okay? I think that's very normal. It's a weird thing to say, talk about the null hypothesis until you've learned it and it's become embedded in your soul that you understand what a null hypothesis is. It's new vocabulary. So what is a null hypothesis? Well, it's the situation that we envision to be the case if there was really no difference between Usain Bolt and Justin Gatlin. And so, wait a second, what does that mean? Imagine there's no difference. What it means is as follows. So let's make this our null hypothesis, which is if Bolt and Gatlin were the exact same person, like we somehow at the starting line were able to put two 100% identical people there, like down to the molecular level. It's sort of like a Star Trek. I put two people right there on the starting line. Nothing different between them. And we say, go. There would be, so envision that world in which these two, in the real world, very different people are exactly 100% exactly the same. Under this imaginary world, it doesn't matter whether it was Bolt here who got this or Gatlin who got this. They were the same person, okay? This is our imaginary world, which we call our null hypothesis, okay? They are identical beings. Now, you remember, if they're identical beings, it just is because we happen to call that one when we teleported them or whatever onto the starting line Bolt, and the other one we called Gatlin. It's not that they were different. No, they were identical. There's no difference between them at all. It's just for some strange reason we decided to call one of them Bolt and one of them Gatlin. And if that is the case in our imaginary world, these differences are just random fluctuations. They're just caused by, there were some pebbles under Gatlin's, for whatever reason, his spot on the track wasn't as good as Bolt's spot on the track. Oh, maybe the wind or the drafting or something affected him, whatever. Remember, he's identical. There's no difference at all. The only reason we have a difference here is because of some random factors that happened while we ran the experiment. We could have called Bolt Gatlin here, or Fred, or Bob, or Mary, or whoever. It doesn't matter. It's just a name. And we could have called Gatlin any name we wanted because they were identical. The only difference is because from the randomness that happened while we ran the experiment. There's just something there that's causing these fluctuations, these differences. It's not because they are different people. That's when we do a null hypothesis, it's all about going into this imaginary world where they're just identical. Oh, and if they're just identical, these differences are caused by randomness. Okay. What we want to do is we want to see if under the null hypothesis, so under our imaginary world, how often would we have gotten a difference this large or larger? If it happens a lot of times, if it seems to be really frequent under our null hypothesis, in our imaginary world where we have these identical people and we're getting these differences, if it seems to be possible to get that difference a lot of times under running this imaginary world where we have identical people, it must not be something that we believe is a statistically significant difference, because it could just happen lots of times. Remember, under our null, they're identical. And so if we get a value this big or greater of magnitude, so it would be more negative, all right, well then, whatever. It must have been noise. It's not statistically significant. We will not declare or believe that Usain Bolt is faster than Justin Gatlin, because if they had been identical, it would have been quite likely by the randomness and the noise present for it. Now, they are obviously not in the real world different. I mean, not identical. They are absolutely different. But it's under this imaginary world that we go and we calculate what are possible outcomes of an experiment under our null hypothesis to understand how likely that could actually occur. So let's show you a way to go about this. This is the approach for what's known as a randomization test. So under this notion that it's just that we labeled them Bolt or Gatlin, we could have gotten a negative result here or a positive result. It's just that these signs could have been different. Whether or not we chose to name one Bolt or one Gatlin, it's just random whether or not the difference was positive or negative. Now, these differences don't change, but whether they're positive or negative is just depending upon which one of the identical runners did we label Bolt and which one of the identical runners did we label Gatlin. So we could absolutely go and make another column here, called, with random signs. And what we do is we go down here and we flip a coin. If it's heads, we say it's a positive difference. If it's tails, it's a negative difference. And we can write down all of those based upon each coin flip tells us whether it should be a positive or negative difference. Because again, under our null hypothesis, under our imaginary world with these identical people, there is no reason it should be positive or negative other than the fact that we chose to name one of these identical people at the line Usain Bolt, and one of them we decided to call Justin Gatlin. So an example for these random signs is, this could be minus 0.08, and then this could be a positive 0.1, a positive 0.04, then a negative 0.06, a negative 0.08, a negative 0.01, a positive 0.16, a positive 0.36, a positive 0.32. And now if that's the case, and we take the mean of this, what we're going to do is we're going to get a difference of a positive 0.07. So this is one possible experimental outcome under our imaginary world, under our null hypothesis. So that could have happened. Again, two identical runners running. It was just randomness that caused these differences. So it just mattered which one we chose. And so this is one possible experimental outcome under that null hypothesis. Now we can do this again. We can make another column, random signs. And we can go down, do all this. And I've done this. And this time I did it. I got a difference of 0.02. And I did it again, said Brittany. Anyway, then we got 0.0, actually a difference of 0. Then I did it again, and this time I got negative 0.04, and I did it again, and this time I got a 0.01. What I'm doing here is each one of these is a possible experimental outcome under our null hypothesis, and we can collect these. We can collect this 0.07, 0.02, 0, negative 0.04, 0.01, and we can do this over and over again. And you can envision, certainly we could do it easily with a computer running a computer code where we're randomly flipping coins, deciding what the signs should be, okay, and then getting these differences, and then taking the mean of them, or whatever our test statistic is. We could do the median, and we would have a whole pile of these, and we could compare them to what happened under the actual experiment's outcome. If we find a large number of them are greater than this, in magnitude, the experimental outcome basically tells us it seems to be random. I wouldn't have faith in it at all. It seems like we can get this big of a difference just randomly. Oh, under our null hypothesis. Okay. So yeah, we will declare it not to be statistically significant. But if it seems to be really, really rare for this to have happened under our null hypothesis, then we have a lot of evidence that may very well be something that we would feel to say, I think this is not caused by random fluctuations and things. I'm going to actually say that this is actually a statistically significant thing. So I've gone ahead and done this. I put these numbers in to the computer, ran the simulation, and I did it 10,000 times. All right, so I can then make a nice histogram. And our histogram goes from a difference of 0 all the way up to 0.15, all the way down to minus 0.15. And I'm not going to draw the separate steps of the histogram. I actually should, so that you actually know. So it is, you're going to get these steps, okay? But again, it's not something I can easily reproduce. So we're just going to approximate this by kind of showing you that we get a distribution, that's kind of like this. You could zoom in if you wanted, all right? But basically, it's centered around 0, and it's fairly symmetric on each side. All right, now recall that we had a value of negative 0.12 for our experiment for the difference. All of these I ran the experiment 10,000 times, and certainly most of the differences are close to 0, but some of them are further afield. And by the way, we'll also hear, I'm about to explain this. But nevertheless, let's take a look. So if we draw this line up, there's a certain number of results that are negative 0.12 or more negative than it. Now, going back to our original experiment, before we ran the experiment, we need to ask ourselves, am I testing whether or not Usain Bolt is faster than Justin Gatlin? Or is it that I actually don't know who is faster? All right, so if it's actually I don't know who is faster, it's an arbitrary choice about whether I subtract Bolt's times from Gatlin's times or I subtract Gatlin's times from Bolt's times. Since it's an arbitrary thing, I could be getting negative differences or positive differences. Only in a circumstance where before you run your experiment, you are absolutely assured that the only difference could be in one direction, and you only have reason to test in one direction, do you ever test in only one direction. If you are just like, I don't know, maybe one is faster than the other, in that case, you need to consider that you could have had negative differences or positive differences. And so we need to actually, if in doubt, you should always be considering two sides, okay? So this is one side and another side. And so you'll see us talk about statistical experiments being two-sided or one-sided. Absolutely, if in doubt, always do two-sided, okay? It's a more conservative approach, and chances are you do not have a legitimate reason to do a one-sided test. Chances are. So if in doubt, do a two-sided test. Now, with that in mind, what about, these were generated from running that coin flipping and doing this, So these were 10,000 data points in here that did this. How often did these occur? All right. So the number of times we got a value that was less than or equal to negative 0.12 or greater than or equal to positive 0.12 was 114. This occurred 114 times out of these 10,000 trials. So let's put this into a p-value, a probability. 114 divided by 10,000. All right, that's equal to 0.0114. All right, so we talk about statistical experiments having a p-value. It's the probability that we would see these experimental outcomes that were the same or greater than what we saw in the actual experiment. And so again, this is what can happen under our null hypothesis. Under the hypothesis that Justin Gatlin and Usain Bolt are 100% identical beings participating in the experiment at exactly the same point in time and everything, this could be the result. These could be all of the various results. Most of the time we get, something really close to no difference, but sometimes we do actually get differences that are as big or greater. But it only happens basically like 1 in 100 times. The probability of this happening in our experiment, in our imaginary world of identical beings, under the null hypothesis, is a very low probability. So, given that it's really unlikely to have occurred by chance, we can say quite confidently that we believe the difference that we measured in that experiment between Usain Bolt and Justin Gatlin is a statistically significant difference. So even though we only had 9 samples, 9 races, it's very unlikely that those differences that we measured were by chance. It does appear that Usain Bolt is faster than Justin Gatlin for that experiment as set up and put together. Please, those of you who don't want to argue sports, please don't contact me. All right, this is just a demonstration of statistics. So this is the way that the randomization test works. Okay, we take our paired differences, we do those random signs, we repeat that, say 10,000, 100,000, whatever you want, but 10,000 is plenty in almost all cases. And then we'll actually measure and see how often that happens, and we'll be able to come back and produce a p-value, a probability of how likely are those outcomes under the null hypothesis. This same notion, though, what's important to note is that when we talk about other statistical tests, such as the student's t-test, the same language exists. There's some null hypothesis that the test is testing. Often it could be, yes, these things are, we're testing the null hypothesis that they are identical. That's what we were testing here, the null hypothesis that they're identical. And we've decided we don't think they are actually identical. It's with very low probability that they're identical. Often there's an arbitrary 0.05 that is chosen as if you are 0.05 or less, you are a statistically significant difference. If you are greater than that, oh, we say you're not statistically significant. But that's a little crazy because 0.06 is not much different than 0.05, but all of a sudden you've gone, it is no longer statistically significant. It is better to report the p-value and let people make their own judgment about whether they want to consider that to be a statistically significant difference or not. Yes, you could report at the typical level of 0.05, this is statistically significant. But you should also always report the p-value so that people themselves can have an understanding of how likely is this under the null hypothesis. So as I was saying, students' t-test is going to have a null hypothesis of its own. Different tests may have different null hypotheses. You should actually understand what those are. Also, the randomization test that I just showed you, as I said, our test statistic, this taking the mean of the differences. We could have chosen the median. We could have chosen some other test statistic, and the randomization test could still be run. Many hypothesis tests, such as the student's t-test, have a particular test statistic embedded in them, and it is not up for us to be able to make a comparison to change it. So student's t-test, the test statistic is the mean. Okay, you can only use it when you are using the mean difference. There are other statistical tests, such as the sign test. There, the test statistic is the number of wins versus the number of losses. So how many times was one greater than the other one? You wouldn't use that test statistic if you were reporting the mean difference, because you were evaluating statistical significance of something that's different. If you measure the mean difference, you need to use a statistical test that uses the mean difference as part of its test statistic. If you are reporting the number of wins, you should use a hypothesis test that has a test statistic that is the number of wins. They have to be matching, okay? Otherwise, you are going to be declaring statistical significance that's not in sync with what you're reporting the difference to be. You can't report the mean difference and run a test based upon the median. That makes no sense, and this is a common mistake being made by people. Anyways, this is the overview. That's what you need to know about statistical testing. I'm going to follow up now with some slides from a paper that I wrote many years ago, and looks particularly at this question about statistical testing in information retrieval, and we'll have that as a separate video. Okay.